Hello, everyone. My name's Tracy Holloway, and I'm a professor in the department, but I'm often based over at Sage, and so it's nice to be here with all of you. It's really a pleasure to be introducing the talk of Cara Scalpone. Cara is a third-year PhD student in the AOS department here. She just completed her master's work, and that's what she'll be presenting on today. Cara will tell you a little bit more about her background before she came to Wisconsin, but I will note that she has had an illustrious career here so far. In 2024, she earned the AOS First Year Graduate Student Award, and actually just this summer, she was awarded an NSF Graduate Research Fellowship, and in fact, this was a hard year for those. There were only 2 atmospheric scientists awarded in the whole country and 1 atmospheric chemist, and that's Cara. So it's a pleasure to present her, and she'll give a talk, and then there'll be questions, and look forward to the conversation. Thanks, Cara.
Well, thank you everybody for being here. I hope the expectations aren't set too high, but I would like to talk about the work that I completed for my master's, helping us understand wintertime air pollution and getting towards the roles of building heating emissions and temperature. So first, I'd like to go through some acknowledgments through my co-authors and the funding. Of course, my advisor is Tracy Holloway, and I worked closely with her as well as Dr. Monica Harkey, a scientist in the Holloway group, for this work. Funding came from the U.S. Environmental Protection Agency, as well as audit settlement funds that were awarded to the Holloway group by the state of Wisconsin. And lastly, my continued funding, as Tracy said, is through the National Science Foundation's Graduate Research Fellowship Program. And as this was completed as my master's, which I finished over the summer, I also want to make sure to acknowledge important people in that process. My graduate advising committee, Professors Ankur Desai and Brad Pierce, were helpful in this endeavor. Pete was endlessly helpful in getting my models to run and be set up, as was Mark Jensen from the Lake Michigan Air Directors Consortium. I also had help from the EPA experts who manage the Community Modeling and Analysis System Forum. And I also want to thank Lizzie Casella, Cece Orth, and Summer Aker, who are alumni of the Holloway group, as well as everyone in the Holloway group, all the AOS faculty and staff, and my friends and my family near and far, some of who are watching today. A little bit about me to get us sort of in context with my work. I grew up in Portland, Oregon. I was there for 19 years, but this was remarkably before fire emissions were much of an issue that my family now experiences. But I went to undergrad in Southern California at Pitzer College, which is in Los Angeles County. And Los Angeles County, for those who aren't aware, is one of the most polluted counties in the United States and has been a long-standing history of being polluted. While I was there, I studied environmental science, mostly focused on ecology, but was very interested in anthropogenic impacts on environmental systems. And that led me to do research, both at the Woods Hole Oceanographic Institute and at the Forest Global Earth Observatory on human impacts on environmental systems. I was particularly interested in modeling, and this led me to the Texas Commission on Environmental Quality. I worked there as part of the air modeling and data analysis team, and that's where I was truly introduced to atmospheric science and air quality. We used photochemical models, the same air quality models and atmospheric models that are used in research, to conduct policy assessments of what human behavior and changes would impact air quality. But I wanted to return to research and understand more about the feedbacks between atmospheric chemistry and processes with human behavior. And that led me to here, where this template is from. Studying in the Atmospheric and Oceanic Sciences Department, as well as being in the Energy Analysis and Policy Certificate Program. As I alluded to, I'm especially interested in the interconnected changes between the atmosphere and human activity and how those impact air quality. So as we've talked about a lot in this room and a lot in classes that I've taken in this department, the atmosphere is a highly variable environment. And specifically, I think mostly about the troposphere and the boundary layer, so the lowest levels of the atmosphere. That atmospheric variability has impacts on human activity, and specifically on our energy use is what I've focused on. Energy produces emissions, which then impacts atmospheric chemistry, and that together impacts air quality. This is a photo of an air pollution event in Los Angeles, kind of my intro to air quality. And for those who were at Jack's talk last week, we also saw how atmospheric chemistry impacts atmospheric variability in climate as well. I will be focusing on the connections between energy use and atmospheric variability in my talk. With energy use, the main pollutants that we're concerned about are those that impact human health. Combustion emissions, such as nitrogen oxides, which are the combination of nitrogen oxide and nitrogen dioxide, are harmful to human health. These are from car emissions, power plant emissions, and home heating emissions. And they have impacts onto respiratory systems and cardiovascular systems. They also contribute to the formation of ozone and fine particulate matter, which have significant health impacts themselves. So NOx emissions and NOx concentrations are highest in the wintertime, but wintertime meteorology impacts both the emissions and chemical processes that regulate air quality. So when we have a decrease in temperatures, we have an increase in temperature-dependent emissions. This is, I think we can all relate to when temperatures become colder outside, we will then increase the thermostat in our homes and have this feedback between outdoor temperatures and what we're emitting from our homes. At the same time, temperature impacts the nitrogen oxide lifetime. This is the residence time that NOx persists in the atmosphere, and it's typically between 2 to 11 hours in the summer, but longer, between 6 to 29 hours in the winter. And that's due to a few processes. Yes, temperature impacts that directly, but we also have a decrease in daylight in the wintertime, both from the zenith angle as well as shorter days. That increases the importance of nocturnal chemistry and decreases the importance of photochemistry. Increasing nocturnal chemistry increases the reservoir species, which are species that hold on to nitrogen oxide emissions and then become re-emitted in the daytime and contribute to higher concentrations in the daytime as well. We also have a lower planetary boundary layer in the wintertime, which can lead to, which has lower winds and leading to lower mixing. And that can lead to concentration of pollution building up, which also can have impacts on nitrogen oxide lifetimes, as that's a nonlinear relationship. I have been focused on building heating emissions because they could be a very important contributor to those high nitrogen oxide wintertime concentrations. However, previous studies that have looked at home heating emissions have focused primarily on wood fire emissions or have lumped wood fire with other emissions together. And the contribution of home heating from other fuels has not been quantified. And to put that into context, wood heating is a primary fuel source for about 2% of homes, whereas other sources such as natural gas, heating oil, propane, those are the majority of homes are heated by those other fuels. Home heating emissions do contribute a substantial amount of NOx emissions in some regions. So what I'm showing in these three plots are, in the top we have annual home heating emissions in, these are tons. So we have the annual home heating emissions from NOx on top with the annual total anthropogenic NOx emissions. In the total NOx emissions, we can see the artifacts of roadways from car emissions, cities have high pollution concentrations, as well as shipping emissions off the coast of the US. And whereas annual home heating emissions are concentrated in primarily the Northeast, you can see, where there's high populations, colder temperatures, and a higher annual home heating. Whereas the Western United States, which is very low population, has a very low magnitude of emissions. When we look at the percent contribution of home heating emissions to total anthropogenic emissions, we can see that two regions pop out. We have a high contribution to those rural regions with very, very low magnitude of emissions. This is like less than 10 to the second to the negative second or lower emissions on an annual basis of total. And the other location that has high contributions are in highly populated regions in the Northeast, and also those are the colder regions as well. And because I'm interested in the health impacts of air quality, I'm primarily interested in the urban air quality and where these anthropogenic emissions are having the greatest impact on human populations. As I've discussed, there are these competing factors between meteorology and emissions that influence wintertime pollution. And we can parse those factors using what are called regional chemical transport models. These can isolate the factors that impact ambient NOx. This is the Community Multi-Scale Air Quality Model, or CMAQ, is the photochemical model that we use in the Holloway group. And this is a regional air quality model, so a 12 by 12 kilometer resolution model with 35 vertical layers and 1 hour time steps. So a relatively fine resolution model when you consider global models or other models that people use in this room. This model ingests meteorology and emissions in moles per second or grams per second, so emission rates, and then as well as initial and boundary conditions, and can simulate the atmosphere to tell us what the NOx concentrations look like. And by performing simulations and experiments within this model, we are able to parse out what the differences between meteorology and emissions are on those final NOx concentrations. But in order to do this, we need to have confidence in our inputs in order to understand the outputs as well. So how are those home heating emissions estimated? When we sought out to answer this question, this was sort of the spot where we started, was hoping to isolate these emissions in CMAQ. We started diving into how these home heating emissions are estimated. So the US EPA develops these triannual national emissions inventories, and they are the state-of-the-art, highest quality emissions modeling that we have for the United States, and is really the state-of-the-art for much of the world as well. For home heating emissions, these are actually the residential fuel combustion emission sector. So it's all of the residential fuel combustion is within home heating emissions. Now, for some emission sources, we have a point location, like a stack, that you can continuously measure. For home heating, this is what's considered an area source or a non-point source. These are estimated for each county, but not at a specific point location, and which is estimated by state level fuel consumed, so data from the U.S. Energy Information Association on how much fuel is consumed. Then that is allocated to a county based on population, and then based on census data on how many households in that county use a specific fuel type. So this is an estimate that gives a fairly confident estimate of the annual total emissions. But to put this into CMAC, where we're getting those hourly variable time steps, we need to temporally allocate in time. And currently, temporal allocations of home heating emissions use fixed seasonal or monthly profiles that do not include temperature. And if we are interested in the temperature impacts and how we can isolate those impacts, we need to be able to include those in this scaling. Currently, we have annual to month profiles that allocate a fixed amount to winter, spring, summer, and fall with a fixed no daily variability at all. So every single day in winter has the same amount of emissions. As we know based on our understanding of temperature, heating season and how often we need heating varies by region and varies the length of time. This was a paper that Gisa Yangji published in 2024. She was an alumni of this department, and she estimated this paper was about future changes in the state level heating and cooling in the United States over time. She looked at this retrospective analysis as well, which showed that the heating season, which is when heating demand exceeded cooling demand, really expands far beyond just those winter seasons into transitional months, such as March and November. In fact, all states besides Florida have heating demand exceeding cooling demand all the way through April. So our method was to apply an annual to day scaling factor based on those heating degree days. Heating degree days, it's kind of a funny term. Heating degree days are an energy-related term based on it's a proxy for home heating. So the concept is that when the temperatures are warm, and above a reference temperature, a comfortable temperature, we don't use home heating. So that's typically 65 degrees Fahrenheit or 18.3 degrees Celsius. And so any temperatures above that, we determine no heating. We assume no heating is required. When temperatures dip below that, heating demand increases proportionally. So a heating degree day is the difference between an outdoor reference temperature and the daily mean temperature. This plot is showing the annual sum of heating degree days from the EPA's 2019 WRF modeling, which I'll get into as one of our inputs. We have hot locations have very low heating degree days, and colder locations have higher heating degree days. This is, I know, kind of an uncharacteristic, unusual metric to see 7,000 degrees Celsius, but this is a sum of the difference between that reference temperature and daily temperature on a given day or across the year. So our approach was to create these annual to day scaling factors for home heating based on that daily temperature. Now, the model that we use for this is the smoke emissions processing software. And what that entails is taking the county level home heating emissions, and we allocate those in time and in space, and we chemically speciate them to map the species from the NEI to our model species. What we've done, and that processing gives the home heating EI with no daily variability. And what we've done is we've introduced the 2019 meteorology from the EPA, extracted the daily air temperatures, and developed temperature-based annual to day scaling factors. And applied together, we have now a home heating emissions inventory with daily temperature variability. To break down that calculation further, the default approach is a seasonally fixed daily NOx value. It takes the NEI annual NOx total and multiplies it by a seasonal scaling factor. And that gives you the seasonally scaled daily NOx. In our approach, we are ending up with a temperature-dependent daily NOx value by taking that same National Emissions Inventory annual NOx and multiplying it by a heating degree-based scaling factor that varies daily. Those daily heating degree-based scaling factors are the fraction of daily heating degree days over the total annual heating degree days for that location. This is also important to note that this is location specific because temperature varies in space. Breaking that down further, I think equations are helpful for context, but I think it's very much more useful to look at 2 case studies on how this was applied. So we looked at a cold city, which was Minneapolis, Minnesota, as well as a hot city in Houston, Texas. These happen to be the hottest and the largest cities in the hot and cold climates that we looked at, but they also were fitting based on my own background as living in Houston and then now living in the Midwest. It was fitting for me, I think. So to go back, we can see that the Houston annual HDDs are very low compared to the Minneapolis HDDs, annual HDDs. So first we took daily mean surface air temperature. This is from the 2019 WRF output, so 1 year of data. And in Minneapolis, Minnesota, our reference temperature is 18.3 degrees Celsius. For much of the year, especially from outside of January through October, we have temperatures less than 18.3 degrees Celsius. So there is some heating demand that we expect. There's also daily temperature variability. We have one day that in the end of January that got all the way down to almost negative 30 degrees Celsius, which we would expect to have greater heating demand than another less cold day. In Houston, we have a different story where primarily the home heating emissions or the heating demand is only in a few months because most of the time temperatures are above 18.3 degrees Celsius. In fact, between March and October, I think end of September, there are no days where temperatures are below 18.3 degrees Celsius. So calculating the heating degree days from that, remember that's the reference temperature minus the daily mean temperature, or it's 0 if the temperature is above that reference. We have higher heating degree days in Minneapolis with those colder temperatures, and much lower heating degree days in Houston. Now for those annual to day scaling factors. So the scaling factors are the fraction of annual emissions allocated to each day. So what that means is that in the EPA default, there's roughly 0.6% of emissions allocated to a winter day, and it's all fixed based on the season. In Minneapolis, we have daily variable temperatures, and this is the scaling factor. So primarily what we can see is that while there is daily variability, the emissions, the daily scaling factors in Minneapolis primarily follow what the magnitude of the scaling that occurs with seasonal scaling. So it's not depending on what you're interested in, this is not a terrible approximation, but given daily variability and the impact on NOx lifetime, having that variability is important. The areas of special interest that we see are a decrease in the scaling factor in September. In Minneapolis, it's closer to 0, whereas in November, we actually have a much higher scaling factor. Otherwise, it's daily variable around those lines. In Houston, the story looks very different. And remember, this is the fraction of annual emissions that are allocated to each day. So in Houston, there are very few days where you have to turn on your thermostat. So there are only a few days where heating demand is required, and those few days are getting a higher fraction of emissions allocated. So the coldest day, one day in Houston may be getting roughly 2% of emissions. All annual emissions go to that one day. And we can also then take that to what the daily NOx emission rates look like. In this plot, I have two select months from Minneapolis. This is the day of the month on the x-axis and the daily NOx emission rates in tons per day on the y-axis. The black lines are the default method, whereas the blue is our temperature-based approach. In January, we can see that some days have lower emissions than the seasonal scaling approach would apply, whereas other days, like that extreme cold day that was almost negative 30 degrees Celsius, has a much higher emission rate on that day. In March, we have the seasonal scaling is much lower than what a temperature-based approach would allocate, where the emissions based on temperature are actually very roughly in the same ballpark as those for January. In Houston, in January, it's a similar story. We have variability around the mean, or the seasonal approach. And I want to also point out that these are on the same scale. So this is just a good reminder that the magnitude of the emissions in Minneapolis is much higher than the magnitude of emissions in Houston, despite those scaling factors being higher. So in Houston, while we have lower emissions, the daily variability around the seasonal scaling approach in January does have a considerable amount of variability. In March, we can see that many days have no heating requirement. So we have 0 emissions allocated to that day, whereas an individual cold day, a day that is on par with the temperatures of January, is going to have a much higher emissions than the seasonal scaling approach. And that is actually the coldest day of the year in Houston was actually in March. So one way to approach looking at this is we looked at the home heating NOx emissions and how this change in daily approach shifted the allocation in time. So first looking at the winter months, the default approach there on top, we have January, February, and December with our NOx emissions in tons. Again, we have very low magnitude of emissions in the west and higher magnitude of emissions in cities, especially in the Northeast. The differences that we see in the default approach, remember these are all the same scaling, these monthly total emissions, the only differences is based on the number of days in that month. If we look at the percent changes, though they look very similar to the naked eye, there are changes in the percent change of emissions that are allocated. So in the winter months, we have a mixed response in how heating emissions are allocated. In colder places, we tend to have a lowering of emissions, and this is sort of a right sizing due to an increased heating season. So those emissions that are higher allocation in the winter are lowered, whereas in warmer areas, we have an increase in emissions in January because that's one of the colder months compared to the others. Looking at spring months, we have March, April, and May. Between the default approach and our approach, we have higher emissions considerably in March and lower emissions in May. You can start to see in the southeast starting to have no emissions in May. But again, a bit hard to see, so we look at the percent changes. In March, we have a nearly uniform increase in the March allocation. And this is to be expected based on that heating season, whereas we have a nearly uniform decrease in emissions in May. becomes even more stark in the summer months with June, July, and August, whereas the default approach allocated some emissions, a fixed proportion of emissions, to summer months. Our approach, if temperatures don't increase above 60 or below 65 degrees Fahrenheit, 18.3 degrees Celsius, there are no emissions allocated to that time. So in many of these regions, there are 0 emissions. Whereas even though there are low emissions in the default approach, now we're having 0 emissions allocated to those times. Please note the scale has changed because by a large proportion because those emissions are so low, the percent change is actually quite high for those places where it's increased. And those places that are increased are in cold regions, where you actually have cold temperatures year-round. So where if you have the seasonal scaling with a large dip in the summer months, if you have cold temperatures year-round, you're going to continue to have high emissions in that time, or it's going to be a more steady amount. But we also have a 100% decrease in many regions. Looking now at the fall months, we have September, October, and November. September, as I don't know if you've noticed, is still quite similar to summer. So September, the emissions in our approach are quite similar to those of summer, June, July, August. Whereas November, which tends to be the beginning of the heating season in many places, are higher than the heating emissions from the default approach. And we can see that very starkly in the percent changes, with decreases everywhere in September, regardless of place. The maximum change is a negative number. And then, whereas in November, there's an increase nearly across the entire country. To look at that as a whole, we have a shift in monthly heating emissions towards March and November, and away from the summer months and the winter months in some cases, to reflect the heating season that is more representative of temperature and heating behavior than a seasonal fixed approach. To understand this a little bit further, we can also think about which month had the greatest increase in the annual fraction of home heating emissions. So which month across the country, where's that fraction increased? For much of the country, November and March, those transitional months to cold weather, had the highest increase. They were underestimated the most out of the other, compared to the seasonal approach. We also had in southern areas where maybe there's only one cold month in January or maybe February as well, we had the highest increase in January. And some of those locations where you have cold temperatures year-round and that really high increase in the summer, we had a highest increase in June. And to see where those emissions are coming from, we can also look at the greatest decrease, or the greatest decrease in annual fraction of home heating emissions. In most locations, that's in September and May, because those are the summer months, or the months that are transitioning to warm weather, where it's still more similar to summer than it is to fall or winter. We also have, in locations where it's especially cold, those emissions needed to be reallocated from winter months towards the transitional months, so we had a decrease in those January, February, December months. Now to return to that annual relative contribution of home heating NOx emissions to total anthropogenic NOx. The importance of looking at the relative contribution is that where home heating emissions are going to have the greatest impact are going to be where it has the highest proportion of total NOx emissions. So this is going to be, our annual home heating on top with the total anthropogenic NOx on the bottom, and our percent contribution to home heating total NOx is higher in the rural regions where there's very, very low magnitude of emissions, of complete annual emissions and of home heating emissions, and in the Northeast, primarily, and other cities as well, but primarily in the Northeast, where there are cold temperatures, high cold temperatures, high populations, and high home heating emissions. If now we can look at how relative contribution changes over time, and what we can see is that the relative contribution, of course, is going to be highest in the winter months. So that annual picture is only one element of the story, but really this is going to be an even greater contributor in those winter months. So we can see that the relative contribution in the summer months is quite low, whereas in the winter months it's even higher than that annual total. Another way that we wanted to look at this was the difference in that relative contribution between our approach and the default approach. So what we can see is that by changing the allocation of when emissions are occurring, we also change how important those emissions are going to be to their relative contributions. This is roughly, we can see the same spatial patterns and temporal patterns of when emissions are increased or decreased, but we especially can see that emissions have the greatest impact away from urban areas, and again in the rural areas in the west, as well as the populated high emission areas in the northeast. And if we look at specifically those the heating season months, because these are the months which do have high emissions, we expect that if we were to look at the contribution of these emissions to ambient air quality, that we're going to have the highest changes in those emissions where the absolute change in relative contribution is the highest. Now just to return quickly to our case study locations, one of the other things that we were interested in is introducing the daily variability in temperature. So what that looks like is that daily emission rates for Minneapolis, our cold location, and Houston, our warm location, both of them have a greater range in values and ultimately much higher maximum emission rates. So whereas we have fixed these are histograms with the number of days on the y-axis and NOx emission rates in tons per day on the x-axis, where our approach are the colored bars and the default approach are the gray bars. In the default approach, of course, we only have four numbers, so every day fits into one of four categories, whereas in our approach, we have daily variability based on daily temperature, as we would expect. One way that we looked at this, I'll just briefly touch on this, is that we evaluated the differences based on climate zones, which is, these climate zones are the definition from the International Energy Conservation Codes, which separates from very hot to very cold based on heating and cooling demand specifically, and then has humidity regions, so humid or dry or marine based on location from coastline and precipitation. And what we saw from this, just very briefly, is that the median percent change, we have, the climate zones on the bottom, so from hot to very cold, with the different color bars representing the different moisture classifications. On the y-axis, we have the median percent change in the maximum daily NOx emission rate, which is that the difference between those highest emission rates, the highest emission rates here, and the highest emission rate in the default approach. So it's that percentage. And we had an increase in that maximum change with higher temperatures and higher moisture classifications. And the easiest way to explain this is that when you have fewer days that need heating demand, so in the hotter regions, then you have a greater increase to the allocation to individual days, which is going to lead to a greater increase in those maximum emission rates. I think I'll breeze by this. I think we can come back to this if anybody's interested. I would love to talk about how this translated to hourly NOx. But just to jump to our key findings, the first and primary key finding is that we have a reallocation of emissions using our approach to March and November, which shifts emissions away from May, September, and other winter months, which more accurately reflects the heating season. The relative contribution of heating emissions or residential fuel combustion there was highest in cold weather months in urban regions with a high magnitude of those emissions, and as well as rural regions with total low overall anthropogenic NOx. And finally, our approach introduced the daily variability in NOx emission rates with temperature, which increased the maximum NOx emission rates. Our future work is, now that we have developed this new emissions inventory, we can return to our guiding question, which was how can we understand what these impacts of home heating have on ambient wintertime air quality. So we can now use CMAQ, that community multi-scale air quality model, the photochemical model, to evaluate our approach and to isolate the home heating emissions impacts on wintertime air quality. Thank you. Okay, thanks. I will just moderate questions. So questions from students first. This is typically how this goes. Yes, Noah.
I have a question regarding like the time scale over which you were taking your emission data. Did you just look at 1 year, or did you space it out over a range?
Yeah, so the input emission data is from 1 year from the National Emissions Inventory. So that's every 3 years, the EPA does a really large evaluation of emissions and estimates all emissions, including residential heating. So what went into the state level purchases and that activity data was 2017 annual emissions. Yeah, Hamish.
How important do you think is human behavior on your results, thinking like regionally and socioeconomic? Like people in Minnesota might not turn the heat on until it gets to -10 Celsius. Like,
yes.
How important do you think that is?
I think that is a very good question and an assumption that I think is very difficult to work in. So what we do know is that people are going to vary differently. So in this, a way that this has been done for residential wood combustion does do that, but bases it on, essentially has a different threshold temperature for different regions. But that's for wood, and it was based on, what's the word? It's based on observations of particulate matter. It was based on in situ observations of when people were burning. And we don't really necessarily have that same data available for this. So we have to make an assumption, and the home heating approximation of heating degree days is pretty well received and widely used. But a more specific assumption would improve this further. Yeah, Jack.
This might be like totally outside of what you looked at, but it's kind of the opposite in that, like, do you know at all what, like, these NOx emissions might be from, when it's actually really hot, when people are running like more simple air conditioning and stuff like that?
Yes. So most of the time, air conditioners run off of electricity. So in the summertime, you have increased in emissions to electricity and power plant usage. So that does have a comparable, analogous response in that there is an increase in electricity usage, which is actually that paper by Gassiangi. She looks at the impact of heating and climate change on cooling degrees, essentially. So it's sort of the opposite. It's, yeah, very interesting. Yeah, Evan.
Could you go to slide 34?
Yes.
I just had a question about, so it stood out to me how much of a difference there is. For example, like in Michigan, it seems much higher, and then that stops at the state border, and then the same thing with Minnesota versus the Dakotas. So I was just wondering if you could talk a little bit more about how those state level, like initial emissions are found before you're doing the county level. Like, is it all reported by state, and do the states get to decide what they're reporting or not reporting?
That's a great question. And so what is going to depend based on individual states, there's a few different factors. So where the emissions are coming from is based on purchases of natural gas, as well as estimates of purchases of heating oil, purchases of propane, all those types of things. But then what you also see on state lines, more so, are going to be what kinds of fuels people are using. So, and that is sometimes dictated based on policy. So if there's heating emissions that are, or a certain fuel type is going to be more used in some states versus other states. So one area in particular is the New England, like Connecticut and Vermont. A lot of their home heating is coming from heating oil still. So that actually has lower NOx emissions from some of these. And I also realized I didn't say NOx emissions is what I'm primarily focused on, but home heating actually has any combustion emissions. So if you have a heating oil is your main source, then sulfur dioxide emissions are going to be a much greater contributor. And if this was a sulfur dioxide map, you would really see that on the state line. That's very clearly a state-specific source.
And then, so for the purchasing, are those purchases, like if the state is generating the natural gas, does it still catch those purchases? So like in the Dakotas, if they're actually cracking and getting natural gas, does it still end up in this?
I would expect so. I would have to double check, but because natural gas is typically purchased from a utility, the utility is what is supplying that information to the Energy Information Administration.
Okay.
Yeah. Yeah, Rudra.
Great talk, Cara. I also have a naive question about your monthly versus daily scaling. In a couple of slides, it seemed to me that maybe just shifting the monthly threshold to a different, not the threshold, but the monthly value to a different mean value might still match the fit of your daily variability. Do you think we should, do we think we still need a daily variation, or just moving the mean based on the location's monthly mean could also give a similar result?
So that is a great point. And actually, since this work, I feel like I planted you, but I didn't. Since this work started, the EPA has updated their methods to use a monthly scaling, and that is based on monthly purchases and is state-specific. So that is a more sophisticated way that the EPA has updated to do since starting this research. But if we're interested in how temperature is impacting wintertime air quality, which is impacting human behavior, then we need that daily variability, especially since the lifetime of NOx is varying on daily scales. So for my research, I definitely want that temperature variability. But if you're looking at larger scale trends, or you're less interested in this specific source, then I think that the EPA's monthly variability is a good alternative.
And I have a quick follow-up on that, because you also mentioned that how important the diurnal variability is, and
Yes.
you had a slide. Is
Yes.
there physically possible, given the is the data available to see how the emissions will change in the nighttime once there's chemistry?
Yes. Well, this is another thing that I didn't have time to talk about today, because it was just sort of a separate thing, was that I showed that diurnal, again, I feel like I planted you. I updated, so the diurnal profile from the EPA's version is this, the purple, the blue. The fixed scaling, we have maximum emissions in the midday and lower emissions at night. This is a default profile, and I talked to one of the EPA experts about this, and this is a profile that is used for many different emission sources if they don't have more specific data. So the fact that they're using this profile, which is not it's not physically realistic to have higher emissions in the middle of the day, was sort of just something that we knew we could improve that assumption on. But rather than going based on temperature, what we did instead was we used a profile that was developed by the EPA to represent wood-fired heaters. So there are no specific diurnal profiles developed for a natural gas boiler or a other type of boiler. But for wood emissions, because they're kind of more focused on, they did have this orange one is what we updated to. So we do have lower emissions midday and higher emissions in the nighttime hours. And perhaps we could talk about this later, but that updating that emission, that diurnal profile, does have a pretty substantial impact on what hours those emissions are allocated to, because it's just a fixed profile that's going to be fixed, but it also has to do with, if we're allocating more to wintertime when there's shorter days, we have, this is an increase in emissions going to nighttime hours. Yeah.
Thanks.
Thank you. John.
Cara, really interesting. Then I know nothing about it. I wonder if snow cover is a factor in, intensifying the low-level inversion, which probably means the chemicals sit around a little bit longer and have time to cook, even though they're out of the sunlight during that time in the wintertime. Is there any plans to maybe put snow cover and exchange on low-level stability into a model?
So that's very interesting. So there are definitely other variables that would be impacting these emissions as well. So like humidity would be another snow cover. Those other meteorological variables are included in CMAX. So once we have the full photochemical model, it has changes in surface, precipitation, humidity. It's a completely full atmospheric model that would incorporate those changes.
So you'd have a chance, if you wanted to really zoom in and specify what particular factor is playing a role in this or that. It wouldn't be emission so much as retention of the chemical in the atmosphere or something, yeah.
Yes.
Oh, that's neat. Okay.
Yeah. Yeah, Matt.
I'm interested in how we communicate health risk. I think I've been making a mistake. You're putting this out. We always talk about ozone directly damaging lung tissue or eye tissue. We always talk about particles less than 2.5 get lodged in the lungs. And those are the two things that I say in 171 and I hear. You're saying that NO and NO2 can directly affect lungs. Are we effectively communicating that? Maybe you guys are. And does it work by nitric acid droplets affecting your lungs, or is it really a NO, NO2 attack on molecules in the lungs?
That's a great question about the physical pathways of how it impacts your lungs. I'm not actually that familiar with the health processes, but we have, in the US, we have what are called criteria air pollutants, and those are the regulated air pollutants that are known to impact human health. So ozone and particulate matter, fine particulate matter, those are really widely publicized because we have regions with very high pollution. So those areas, there are regions in the US that have ozone and particulate matter pollution that exceed health standards. For NOx, or NO2 specifically, that is also one of the criteria air pollutants. It is directly harmful to human health, but we don't have areas with high enough concentrations of NOx that lead us to need to regulate that more specifically. But NOx also is a precursor for ozone and particulate matter. So we need to be able to isolate these impacts both for their own health impacts, but also their impacts on ozone and particulate matter. Yeah, okay.
I have a question, and you might have rushed through the slide at the end.
Sorry.
But it's the days of the week.
Oh, yeah.
So in talking, with energy folks, I know that day of the week matters, especially is energy usage going to be more in the home place or in a commercial place? But clearly you're interested in house, emissions, home emissions. So I'm wondering if you can say anything about that, and then also I'm wondering if there's anything about I know that holidays are really big in terms of electric usage, especially in houses. So I'm wondering if you saw any signals for that in your analysis.
That's a great question. So one of the reasons I did focus on residential heating versus commercial or industrial heating, which are they're also estimated in the NEI, but we as individuals are more likely to control our daily variability based on temperature, whereas a commercial building, they might have central heating that isn't as variable and maybe is more variable based on the day of the week. Maybe it's only operating at a fixed value during open hours and then not on the weekend. I didn't specifically look at, what emissions are variable. I only looked at the temperature impacts and not on how, if people are home, if that's higher or lower. But that would be definitely interesting, especially if we're looking later and comparing our photochemical modeling results to observations to see if we are doing maybe a better or worse job on the weekends versus the weekdays, if there is a difference there. Yeah, Brad.
The changes in March in the Midwest are really interesting. I think we'll have a lot about wintertime nitrate and things. So I'm wondering whether you've thought about introducing all this really nice weather-driven variability. Do you think there's ways that you could validate that with satellite data?
Yes. So actually one of the ways that this was started was by Monica Harkey was looking at whether we can see the signature of building heating in satellite observations of NO2. We have Tropomi, which is a satellite that detects NO2. So these are satellite detections on the y-axis and average daily maximum temperature, specifically for the counties that have really high relative contribution of home heating. And we do see that there is the increase in NO2 abundance with colder temperatures, but and we're interested in looking at how we can we can see that it's a very complicated signal,
Yeah.
and we want to be able to look at how satellite data can how basically what we can see from space is influenced by home heating as well as the meteorological variables.
Yeah, I mean, I would think you certainly see, after precipitation, you see soil NOx bursts.
Mm-hmm.
And I'm wondering whether during cold spells you might see some signatures of this, not average daily, but actually
Yeah.
time series.
I think that would be very interesting, especially like you said in the March, November,
Right.
when you maybe have people turning on and off their heating
Yeah.
more than in the winter if it's just constantly on.
Yeah.
Thank you. Probably one more. Yeah, Noah.
So I just had a thought about maybe factors outside of ambient temperature that have an effect on your home heating load, like when if it's raining, like the more time inside is becoming. Did you consider other factors that might be related to home emissions?
That's a great point. And I didn't consider other factors, but yes, precipitation would impact how much people are using their heating. Wind speed impacts how much people are using heating. Humidity as well. So using heating degree days that as a temperature for home heating is only introducing temperature variability. But we do know that that is going to impact other variables are also going to impact human behavior. Yeah, it's a great point. Yes, Tracy.
Well, I just wanted to say, that here in Madison, there's a group called Slipstream, and they do building modeling, and they do a lot of work to look at how do all these external factors actually affect how people are actually using it inside the house. But every house is different, so a national scale analysis like Cara is doing could leverage that, but that would be, there's just a lot, these are all great questions, but I just note that indoor air quality and heating modeling is kind of its own field of engineering in itself that takes AOS type inputs as inputs to their models. So, thanks.
Yeah, great point. Okay, I think that we can call it there. If anybody has questions for me, I would love to talk more about this. But thank you all for coming.